Let's investigate finding volumes by cross sections. And we'll start off by looking at, considering a cylinder, because this might be a place to help us to get an intuition about what's going on. We know how to calculate the volume of a cylinder, and let's suppose this is a right circular cylinder. We want to get the area, or the volume of this cylinder, so we just take the area of the base times the height. Well, we know how to do that. But let's suppose we take an alternate approach, and let's suppose that I cut a smaller cylinder out of it. Okay, so I just cut down through here and cut a piece out, where a piece that has a thickness of delta x. And let's look at the cross section over here. So here's the piece I cut out right there. Now it's got, of course, the radius, r, and it's got a thickness. The thickness is delta x. We can't see it, but it's going into the paper, right? So if I want to calculate the volume of this little piece that I cut out, this little cylinder, it would be pi r squared times the thickness, delta x. That would be the volume of that. Now, I could go ahead and say, okay, I'm going to cut more out and calculate the volume of each one of these, and then I could just add them all up. I could add up all these volumes, and I would get the volume of the cylinder. Yeah, I could just add up all these little volumes of all these little cylinders that I cut out of it. That would be one way I could do it. And that would be, madness. That would take too long. We know how to calculate the volume of a cylinder, a right circular cylinder, but what about if we have a solid that's a little bit more interesting? Let's suppose that we have a solid described this way. Its base is bounded by y equals 0, y equals x squared, x equals 0, and x equals 1. So let's see what that would look like. Okay, so I'm just talking about the base of this solid right now. Let's suppose we have a solid and we're looking from above. We're looking from above down at this solid, and this is what the base would look like. Okay, it would look like this right here. So we've got this solid, and it's all built on a base like this. Now here's something else about this solid, and this is x squared right here. F of x equals x squared, let's say. Now let's suppose there's something else about this solid. If you cut this thing, if you make a cut perpendicular to the base, so I've got this solid here, it's coming out here off the paper. If I cut perpendicular to this base and look at it, look at any cross section, the cross section, let's suppose, is going to be a square. So let's suppose that's the kind of base we have. I don't know if I can draw this, but we'll see. Let me see. Okay. Okay. So anyway, we have a square coming out. We have a lot of those, right? So in other words, this is the quality of this solid. The cross sections are all squares. So for example, let's look at this one right here. So we cut this thing, get a cross section, and all of those cross sections are squares. So what is the area? What is the surface area of this square? Well, it's this length squared, right? Well, what is this length? From 0 down up to the function, it's going to be x squared squared, right? That's the area of this. Now we've also got the fact, we know that this thing has some depth to it, right? So we've got to consider this part right here. Well, this is delta x. So if we want to talk about what is the volume of this little cross section, if you just took a little cross section, took some thickness to it, what would it be? Well, it would be x to the 4th times delta x. And that would be the volume of this little thing. Well, what if we want to do that for this whole solid? We want to look at all these little cross sections. and we would calculate the volume, and I would add up all those. Okay, so I want to add up all these. Well, the smaller the delta x is, the better approximation for the volume of this solid we would get. Well, what we want to do is we want to let delta x go to 0, and then we're back to integration. We've got x to the 4th dx from 0 to 1. And that would be the volume of this solid that has this property. It has this base, and the cross sections are all squares. See? That's what it would be. So in this case, it would be 1/5. Okay? If we went ahead and integrated that. So that would be the volume of this thing. Now let's change it a little bit. Let's consider the same base. Okay? Same base. But the cross sections are going to look different. Okay? So here is our base. There's f of x equals x squared. And this time, the cross section, every cross section perpendicular to the base is going to be, let's say, a half circle. Okay? So in other words, I've got this shape down here. Here's the base. And coming out here are these little half circles. So let's look at a cross section. Let's suppose I take a cross section right here. Okay. Okay. And let me just draw it over here. Here's the cross section. Here's us looking at the cross section right there. So this part right here corresponds to this. And this part here is coming out. Let me see if I can draw it. Yeah, it's coming out like that. Okay? And then of course, all the cross sections are like that. Okay? So here we're looking at a cross section. And I want to get the volume. So what would we do? How would we calculate the volume of this shape? Well, I'm going to look at this cross section. Okay, here's the cross section. And I want to calculate the area of this cross section. Well, it's pi r squared, 1/2 pi r squared, 1/2 pi r squared. That's the area of a semicircle. And then we're going to take, of course, times the thickness. Okay. Well, what is r? Well, for this half circle here, r, well, the diameter is x squared, right? So r is actually 1/2 x squared. Okay, it's 1/2 x squared. So let's see what we have now. We modify this. 1/2 pi times 1/2 x squared squared. See? 1/2 pi r squared and delta x. Okay? Now, we're going to add up all of these things, all these little volumes. So what we have is, what it amounts to is, we're going to integrate from 0 to 1, and I'm going to put in the formula for the surface area. You can think of it as surface area. I've got 1/2 pi times 1/2 x squared squared dx. So in other words, what I'm doing here, you can think of it this way. I'm integrating from a to b. Whatever, in this case, our a is 0 and our b is 1. And I'm taking the area. I'm taking the area of that cross section and just integrating it. That's what I'm doing. Notice this is the area of the cross section. Up here, the area of the cross section was right here. It was x squared squared. Okay? But that's how we do this. Now, to finish this off, of course, we would just have, this is 1/4 times 1/2, that's 1/8 pi. Okay, I just took all that out. X to the 4th dx. There we go. And of course, this goes from 0 to 1. So we have pi over 8. And this is 1/5 x to the 5th from 0 to 1. Or that's pi over 40, I guess. Yeah. So that would be the volume of that particular shape. Okay, let's look at one more. Let's suppose we've got the same base. Okay, there's a base here, and there's shapes coming in here. And let's suppose that every cross-section that we observe perpendicular to the base, so we make a cut straight down. We look at the cross-section. Let's suppose it's a quarter circle. Okay, so in other words, it looks something like this. Okay, quarter circle. There it is, a quarter circle. And this right here is that part. So we're just looking at this cross section. Now remember, the name of the game here is to figure out what the area of that cross section is, because this is going to be 1/4 pi r squared. That's going to be the area. Okay, 1/4 pi r squared. Well, let's think about this. This length right here is x squared, and that happens to be the radius in this case. In the previous example, that was the diameter, and the radius was half of it. But in this case, if it's a quarter circle, that's the entire radius, right? If you think about it. So the area then is going to be, a of x is going to be 1/4 pi x squared squared. Okay, pi r squared. Yeah. So if we then set up the integral, it's going to be 1/4. Okay, pi. Okay, 1/4 pi x to the 4th dx from 0 to 1. Yeah, no worries. Now we've got this. We've got pi over 4, the integral from 0 to 1, x to the 4th dx. And then that one's no problem to integrate. We've got pi over 4, 1/5 x to the 5th from 0 to 1, or that's going to be pi over 20. That's how it's going to work out. So there. So notice every time, the name of the game here is, they'll give you a base, and they'll say the cross sections are half circle, quarter circle, square, rectangle. Whatever it is, you have to figure out, well, what is the area of that cross section? If I'm looking at that cross section, what is the actual area that I'm looking at? How can I calculate the area? And you use the base to do that.